Some beautiful stuff. All right. Looks like we are a go. So good morning, everybody. I'm Bruce Nietzsche. No, I am not Bruce Nietzsche. Bruce is out of town. So I get the pleasure of welcoming you all to this morning's Grand Rounds and introducing my dear friend, Quinn Buchlak, for today's lecture. Instead of sharing all of his amazing accomplishments, I'm going to just tell a little story of how Quinn came to be part of our world and sort of share with you and reflect on what is possible in this amazing healthcare community when people do what they love, enjoy it and do it to perfection, and then share that love with everyone else. So Quinn was in Seattle now 8 years ago, supporting his brilliant wife who had a stint at Boeing. And as he's got this problem with not being able to not learn for more than 30 seconds at a time, he volunteered at our hospital to learn more about healthcare. And so as he's up on the floor volunteering, he runs into our previous CNO, Allison Bradywood, who says, "You need more input than what is available on this side of the street," and brings Quinn over to the neurosurgery department. Quinn spends a half a day in clinic, incessantly asking brilliant questions from someone who's never been in healthcare. The next day, he goes to J.C. Levesque and Raj Sethi's OR and watches a complex spine case and in OR 15. And if you guys have never been in OR 15 or had never been back in those days, it was a party. And all the people in that space were passionate about what they were doing. They were having a great time and they were more than excited to share. So I think that bug was transferred to this man. And then Raj and Julie Katz created a visiting scholar position in the neurosciences department so Quinn could do some research with us. And the rest is sort of this rapid fire history of amazing things. Vijay Yanamadala, our first complex spine and VMPS fellow, was here at the same time. The synergy between Quinn and Vijay was amazing. They published a ton of papers and did some brilliant work. And then Quinn went back to Australia, did an MD, did a PhD, I think the first PhD in AI and neurosurgery, and started a neurosurgery residency, which are all minor accomplishments. His true accomplishment is he created two amazing creatures that are now running around home with Kel, his wife. And we are privileged to be part of his continued work in neurosurgery and to share his friendship and his family. So I will leave you with that. And remember, as you hear all this amazing stuff that Quinn does, that each of you are inspiring this in others every day. So keep it up, keep enjoying, keep perfecting. And Quinn, I'll give you the stage.
Good morning. Thank you so much, Dr. Faruqi, for that introduction. You're too kind. It is a real honor to be here, to be invited to speak about machine learning and neurosurgery. Thank you very much for your time. It's a great privilege. So let me take you on a journey. I'd first like to start by thanking just a few of the incredible people I've had the opportunity to work with. It has been an amazing journey. Many people have contributed to the good work we do, and I just feel privileged to learn from these incredible people. So thank you from the bottom of my heart. I like to ground on good values when I get the chance to speak about these things. So I think the best advice I ever received when stepping into medicine was to be humble, and it remains the best advice. I think everyone deserves respect, and it's important to have courage. So why is it worth speaking about machine learning and neurosurgery? Well, it's a powerful technology. We've all heard about it, and there's a lot of hype. And I think probably we're all in this position of complexity right now. We know a lot about AI and machine learning. We've heard a lot about it. But what I'd like to do today is to help bring us a little closer to clarity, if I can. So we'll talk a bit about what machine learning is, what it can do, and we'll take a look at the near future of applied machine learning and neurosurgery. So who am I? I'm from Australia. It's a long way away. It's a long flight. This is Melbourne, my home city. It's a great spot. I recommend visiting if you get the chance. a city of great food, and I've had the opportunity to learn from some incredible institutions, Virginia Mason being one of the biggest and most important ones. So thank you. This is a sort of a summary of my career. So I started life as a management consultant. I was in consulting for 10 years, and that was focused on working as an organizational psychologist, so predicting performance at work and predicting organizational success. I then moved into clinical research and became a doctor, significantly because I was inspired by the team here. Did an MD and a PhD and shifted the predictive modeling work to predicting patient outcomes. And then more recently, I've had the privilege and the opportunity to be a device industry executive, classifying image pathology and working on software as a medical device based on deep learning. This is a photo of me about 8 years ago working as a clinical researcher here. It's wonderful to be back. And as Dr. Faruqi said, it was a very productive time. I'm really proud of the work we did back then and the work that has continued since. I need to declare an interest, so I'm a part owner of this company called Harrison AI. We develop deep learning systems for pathology and radiology. So let's look at some of the contextual factors that are influencing applied machine learning in neurosurgery first. If you input these search terms, so machine learning in medicine and machine learning in neurosurgery into PubMed, you'll see these hockey sticks pop up. The number of publications is increasing significantly over time, and we're still in the early days of applied machine learning in medicine. This same trend is borne out in the systematic reviews that we've completed. So we conducted one on decision support in neurosurgery, and this is broken down by applied algorithms. You can see the number of publications is increasing very quickly. Same with NLP applications in the clinical neurosciences. Healthcare AI funding, so investment and venture capital is increasing over time. And the number of startups is exploding. Many new ideas, a lot of consolidation. It's a rapidly shifting market. You can see here the number of FDA clearances for software as a medical device, AI systems, and that also is increasing rapidly and significantly over time. So Harrison AI, the company I mentioned, we raised $129 million a couple of years ago, the largest Series B in Australian history. To create these AI systems for medicine. This is an NVIDIA GPU, one of the most advanced chips that is driving this AI revolution around the world. This is the A100. They cost $10,000 each. And this is NVIDIA's stock price. So NVIDIA was briefly worth $1 trillion thanks to the AI boom, and it gives you more of an insight into how significant this AI revolution is. Inflection AI is a newer company created by the head of AI at Google. It's based on a large language model, and they just invested $1.3 billion in NVIDIA's AI chips. So it's a huge industry. The AI and healthcare market size is projected to become worth approximately $190 billion by 2030. So this is a huge wave, and it's changing the world. The technology, machine learning, is complex, but its function really fundamentally is simple. It's based on 3 core factors. The first is advanced algorithms, the second is powerful compute, and the third is clean and voluminous data. And it brings those things together to achieve this function of prediction and classification. So prediction is about deciding between multiple labels at a future point in time, whereas classification is about doing that at this point in time. So there's a few different kinds of machine learning. Supervised learning involves training algorithms with labeled data. So you may have a data set that is labeled with complications for surgical patients, so complicated, not complicated, and those labels are used to train the algorithm. Unsupervised learning involves discovering structure in the data and clustering data, and reinforcement learning involves comparing the outputs of an algorithm to a certain benchmark and applying rewards to optimize performance, and that's used a lot in robotics. But this really is what it's all about. It's about precision medicine. So if you take patient data, a lot of patient data, you prepare it, clean it, use it to train and evaluate your model, and then deploy this optimized model. You can take new patient data, run it through your trained model, and yield these outputs. Get precision diagnostic information and move medicine towards a personalized future. So this is a good example to help illustrate that. This is a system we created about 8 years ago. 8 years ago, it's the S3. It's a simple algorithm that was designed to predict 30-day complications post-complex spine surgery. You can see I can put an individual patient's information into this system, and it gives me a specific risk score for that individual patient that then helps them to decide whether surgery is appropriate for them. And that's really what this machine learning revolution is all about. It's about personalized precision medicine and precision diagnostics. This is a useful slide that explains the process in detail. So let me share with you how supervised learning works. Up here, you've got training and testing, the training and testing process. And down here, you've got the prediction and inference process. So if you take your data set, the first thing you do is split it into your training data and your testing data. So usually an 80-20 split. You've got labels against each of your cases. That might be, this patient experienced complications versus not. You extract features, put that data into your algorithms. You can select from many different kinds of algorithms. You train your model, you tune it, and then you evaluate it by running it over your test data set. There are many different performance metrics you can use. K-fold cross-validation is an important process, and then you can do external validation as well on data sets from other states, other countries. Once you have a model that is optimized and appropriately performant, you can implement that into practice. Then you take new data from a single patient, go through the same data cleaning process, run it through your model, and then you get the gold, which is the new labels, the personalized risk stratification, the personalized output of the machine learning model for that individual patient that then facilitates decision-making and diagnostics. This is an illustration of K-fold cross-validation. So just running through it quickly, you take your data, split it into the training and test data sets that I mentioned before. Then you take your training data and you split it into 5 different blocks. You train your algorithm on 4 of those segments and hold out 1 for testing. Then you repeat that for each of the folds and average your performance over each of those 5 folds. And that gives you a more robust indication of the performance of machine learning algorithms. So that's K-fold cross-validation. Performance evaluation in machine learning is very much based on this idea of the confusion matrix, very familiar to all of you, I'm sure. A good model is one that demonstrates high true positive and true negative rates and low false positive and false negative rates. The AUC curve, of course, as you, I'm sure, are familiar with, is a mainstay of model evaluation. So if you create a model that is unable to differentiate between a couple of groups, so the red dots and the green dots, then it's a random split, and the area under the curve is is low. If your algorithm can separate some cases from each groups, then the AUC is higher, and if you've got a perfect split, the AUC is 1, and it illustrates the diagnostic ability of a binary classifier. So the AUC curve is used a lot in machine learning. There are many different kinds of algorithms, so logistic regression, support vector machines, random forest, gradient boosting machines, and neural networks. They're all different ways of combining data statistically to achieve that prediction functionality. This is what a deep learning neural network looks like. You've got an input layer that can be as large as you like, multiple hidden layers that process the information and extract features, and then an output layer that gives you that label, that prediction that you're after. So complications versus no complications, or improved quality of life versus not. So you've got this overarching umbrella term that is artificial intelligence. Machine learning sits within artificial intelligence, and deep learning sits within machine learning. And the real value of deep learning is that it is far more accurate than anything that has come before, and that's partly why everyone is so excited about it. So let's look at model inputs and outputs. We're all familiar with this idea that data is numerical, right? Think of your Excel spreadsheet, but images, words, video, audio, it's all data. It can all be converted to numbers and used to train these algorithms. So we know what numerical data looks like. This is how it can be structured. So you've got 1D tensors or a vector. You'll hear this idea of a vector used a lot in machine learning. 2D matrices, so your Excel spreadsheet, you've got 3D tensors, 4D, 5D tensors as well. They're just different data structures that can be used to train algorithms. So how can images be converted to this kind of data to train algorithms? Well, this image gives you an idea of how they can be converted for for that process. So each pixel has an intensity. You convert that to a number, then you can feed it into your algorithm. You can encode color channels in a similar way. So you've got a 3D tensor here that encodes color. And like I said before, you feed that into a deep learning algorithm. It extracts features, builds some level of understanding around what the image is, and then is able to give you a useful output. This is a depiction of a convolutional neural network, which is really the standard or the state of the science for image classification. You can see that the algorithm looks at different segments of the image, extracts features, and then is able to classify different objects within those images. So it's a convolutional neural network. So words can also be used as data. The field of natural language processing sits at the intersection between computer science and linguistics. And it can be used for text classification, natural language generation, information retrieval, and natural language understanding. And this is really a very exciting area right now. I'm sure you've all heard of ChatGPT and GPT-4. That all sits under this umbrella of NLP. Here you can see some older, more traditional models. So BERT is one. It's a neural network with 340 million parameters. It was trained on 16 gigabytes of text data, and text data is quite light. So that's a lot of text. That's 3.3 billion words, and that was used a lot a few years ago. Google developed T5, which has 770 million parameters, was trained on 750 gigabytes of data and 155 billion words. So that's NLP, and there's some example models in NLP. And all of this is based on the programming language Python. So just remember that machine learning is based on these three core factors: algorithms, compute, and data, and it's all about prediction. We're talking about a set of technological tools here that can improve medicine, make it more precise and personalized. And a key issue that you hear a lot is this fear of automation, right? And I contend still that we're talking about augmentation rather than automation. I think this is all about decision support. It's about making us better at what we do, better clinicians, better decisions, safer, more efficient care. I don't think the concern around automation, I think it's more complex than that. So let's take a look at some applications in neurosurgery. We're lucky that our field is a data-rich environment, which lends itself really well to the application of machine learning. So in neurosurgery, we can use it for diagnostics, decision support, risk stratification, treatment planning, cohort identification, device optimization, EMR data mining, and precision medicine optimization. These are a couple of examples, recent examples of machine learning applications within neurosurgery. So it's been used for prognosis and immunotherapy response in glioblastoma patients. It's been used to predict the timing of discharge and discharge disposition in neurosurgery patients, to predict outcomes for ACDF patients, predict the likelihood of hyponatremia post-transsphenoidal surgery, mortality, survival, long-term outcomes after SAH treatment. It's been used in spine surgery, many different applications, different outcomes predicted, and used to predict readmission after spine surgery as well. So I'll double click on a couple of these examples, and we can discuss some applications that I think are particularly interesting. So this group predicted mortality in patients with basal ganglia hemorrhage. And you can see based on these performance curves that the algorithms performed very well. Some of our work involved predicting complications after deep brain stimulation. Again, you can see the performance was reasonably strong. Our group in Australia predicted quality of life after pituitary surgery. And this application is really interesting. So this team, Cardone and colleagues, developed a system that's able to accurately detect and show pathological tissue in real time for glioma resection. So what they've done here is they've taken operative videos, they've trained an algorithm to identify tumorous tissue, and then the system is able to be used intraoperatively to isolate that tissue that can then be resected. So that's an interesting use case and an example of how these kinds of systems can be used intra-op. So this example I think is particularly interesting and is a good example of how significant the change can be to the profession. So this group developed a system to subtype, grade, and segment glioma on radiology scans, so MRIs. And the really cool thing about this is you take an MRI, you have a trained algorithm that analyzes that image, and it gives you a genotype, right? Like you're automating the process of a biopsy with a machine learning algorithm, which eliminates the need to perform a brain biopsy for this patient. So this kind of system, has the potential to eliminate the need for an entire surgical procedure. That's kind of the power of this technology. It's and you know, one of the more significant changes in the nearer term, I think, for our specialty. So eliminating the need for brain biopsies, it's quite interesting. We did some work on risk stratifying patients with aneurysmal subarachnoid hemorrhage. So we trained some algorithms to predict acute clinical outcomes, you know, whether or not patients need surgery, whether they will go to the ICU, their risk of mortality, and their likelihood of different discharge dispositions. And we created this. The first step was to train the algorithms, and then we created this simple scoring system that can be used at the bedside. You know, one of the challenges with machine learning is implementation. So these simple scoring systems can be useful. So this is an example of a CT scan, obviously. There is a significant pathology on this scan. The Harrison AI team developed a system to detect 144 clinical findings on CT brain scans. The pathology on this scan was missed by 30 out of 32 radiologists in our validation study, but the AI picked it up. So you can see that there's a large parietal occipital stroke, ischemic stroke here, and it's confirmed on MRI. This is another example of the AI picking up, you know, IVH on this scan, and these are the results of that validation study. So the AI, you can see down here, we've got the parent findings on CT, so ventricular effacement, subarachnoid hemorrhage, cerebral edema, etc., extraaxial mass. You've got the AUC performance down here, and you've got the three conditions. So unassisted radiologists, assisted radiologists who had access to the AI, and the AI alone. So you can see that the green AI alone demonstrates the strongest performance across all clinical findings always. Unassisted clinicians demonstrate the lowest performance, and then assisted clinicians are in the middle for all of the clinical findings. This is a very strong effect that's you know, replicated time and time again in the literature. So you can see basically this tells us two things. The first is that AI makes us better as clinicians, improves our performance, and the second thing is it makes us more efficient as well. It helps us to save time. We can treat more patients with the time we have. Excuse me. This is a 3D representation of a particular case. So what you can see here is a CT brain scan represented in 3 dimensions with multiple clinical findings. So there's hemorrhage, edema, midline shift in this case, and this is the ground truth determined by a subspecialist radiologist. And these are the predicted findings detected by the model, and you can see that they align quite well with the ground truth. So the model performs well. So what's also interesting is, so we've seen how machine learning can be applied to numerical data to predict outcomes, how it can be applied to imaging data to facilitate diagnostics, but you can also apply it to text data to facilitate the systematic review process. So we wrote this review on machine learning applications to glioma detection on MRI. We went through the laborious process of going through, you know, thousands of articles and deciding whether or not to include or exclude them. But once you finish that process, you've got a column in your spreadsheet that's just ones and zeros. And that's a simple classification problem, right? So you can use that data to train an algorithm to do that task. So that's what we did. So we trained BERT and a collection of other NLP algorithms to automate the systematic review process with that hard work and the data we generated. And you can see that they perform quite well. So we've done that a few times now. And the thing that excites me about this is that you can either do a systematic review once or take one that already exists, train an algorithm, repeat that at a future point in time in 5 years, and get it done in, you know, weeks instead of months. I think that's really exciting. So, you know, some NLP applications in the clinical neurosciences. So it's been used for patient cohort identification, automated reporting, data information extraction, literature synthesis and outcome prediction. So Zhang processed 4.2 million patient records to identify patients with aneurysms. Zanatti analyzed health records to identify patients for inclusion in a study decreasing the rate of aneurysm growth by administering aspirin. Kahay developed a system to process clinical notes to predict wound infection. Senders have developed a system to extract clinical text to identify features associated with glioblastoma. Singh did topic modeling in spine surgery across 25,000 articles, and Danilov used NLP to process over 100,000 operative reports to predict the duration of a patient's post-operative hospital stay. Very diverse applications, gives you an insight into how broadly applicable this is. An example use case of NLP can be seen here. So we've got two different abstracts from a couple of different articles. We ran them through the T5 large language model, and you can see that it synthesizes the information, summarizes the information really well. So the output of the T5 was, surgical site infections are a major driver of morbidity and increased costs in the postoperative period after spine surgery. This study developed NLP algorithms for automated reporting for wound infection requiring reoperation after lumbar discectomy. So the language is, professional. It's able to summarize these things well. So if we take a step back, this is a useful framework for thinking about developing research questions and applying machine learning in neurosurgery. So you've got data sets down the left, you've got your different kinds of machine learning in the middle, and then the outcomes that you're interested in on the right. You can basically link up any of these to come up with an innovative study and an innovative research question. So you can take radiology images, run them through supervised learning algorithms, and achieve diagnosis, or you can take your clinic notes, run them through NLP, and predict readmission. So let's shift our attention now to generative AI. This is a really exciting area that is going to change quickly, is going to have a significant influence on medical practice, I think. So OpenAI is the company to watch. They developed this system called GPT-3 a couple of years ago. It's a large language model. We saw these older models before. GPT-3 consists of 170 billion parameters, and it was trained on 500 billion words. And it's difficult to really understand what that means. And I think this helps, right? So GPT-3 has been exposed to approximately 16 times more information than the average person throughout their entire lifetime, right? That's significant capability. So at the time, it was lauded as being amazing, humbling, more than a little terrifying, one of the most interesting and important AI systems ever produced. And it could be used to produce prose, code, and poetry. So we tested it at that time. This is about 2 years ago. And we asked it how machine learning changed medical care. And it provided this response. I'll just read it out. So, in the future, there will be a connection between a person's medical records and their electronic medical records. Machines will have to know all the necessary information about their patient to be able to identify and diagnose. They'll use a deep learning process where they'll learn by comparing a person's medical records with other records. They'll learn about the person's medical history and what the person's body is like. They'll also be able to recommend the best course of treatment. What you'll notice about this language is that it's quite elementary. It's a little bit circular, and it's not that impressive. We asked it we ran a couple of jokes through it, and it's got room to move with regard to sense of humor. It wasn't that impressive there either. So recently this system, GPT-4, has been released, and this is a big deal, right? So if we see GPT-3 here that we just looked at, GPT-4 consists now of 1 to 100 trillion parameters. The amount of data it was trained on is unknown. We don't know, that's not shared. And GPT-4 is at least 1,000 times larger than GPT-3. And here are some examples. So I think one of the interesting use cases for these, significant synthetic cognitive systems is education in healthcare, right? So I asked it to write a short paragraph about a patient presenting with an aneurysmal subarachnoid hemorrhage with correct signs and symptoms. And it produced this, right? So it said a 54-year-old woman presented with sudden onset headache, thunderclap in nature, transient loss of consciousness, neck stiffness, photophobia, vomiting, brief episode of confusion, and a GCS of 14. It talks about investigations, and it has the diagnosis there. I think this is quite impressive, right? Sure, there might be some obvious stereotypes like the thunderclap, like it's not subtle, but it's much, much better than I think anything GPT-3 could produce. Here's another example. So write a short paragraph about a patient with a glioblastoma, and here is what it produced. So 58-year-old man, 3-month history of progressive right-sided weakness, worsening headaches, confusion, changes in personality, hemiparesis, etc. It has investigation results and that diagnosis down there. So again, another really interesting, credible, useful example of a vignette that was produced in a second by this synthetic artificial intelligence, right? This is also a compelling use case of these kinds of systems, and that's the diagnostic use case, right? So what I did was I took that GBM description that the model produced and I ran it through and said, these are the signs and symptoms. What do you think could be wrong with this patient? What are your top 3 differentials? And it came up with the factor that could be a brain tumor, a stroke, a neurodegenerative disease, and it has some additional differentials down here. But it also has, so I think this is quite amazing. It's got credible differentials. It's got some clinical justification under each one. And then it has investigation recommendations as well, right? I mean, this is an artificial, intelligence algorithm without, specific medical training. I think it's quite impressive. This is another really interesting use case that I thought might interest you. These kinds of large language models may help drive innovation in neurosurgery. So the first step here, I asked it to describe the ACDF process, and this could be any procedure, right? Glioma resection, et cetera. And it did it well, right? It outlined the entire surgery. I've stripped out a lot of detail so as not to bore you more than is completely necessary, but the process was accurate. I then asked it, how can we improve the ACDF process? And it came up with a collection of ideas, right? So enhancing images, biological advancements, improved hardware, improved post-operative care, and appropriate patient selection and preoperative planning, right? Including this idea of prehabilitation, which speaks to the innovations of this institution, right? Like the Neurosurgical Conference. So I think that's quite interesting. And then I pushed it a little harder. I double-clicked on this and said, okay, that's great. Can you give me some ideas around how I can improve hardware to optimize the, this kind of spine surgery? And it's come up with some really interesting ideas. Now, I don't have the, the clinical engineering sophistication to be able to determine whether these things have been done or are possible, but they're interesting ideas, right? So it's suggested using biocompatible and radiolucent materials, using materials that better mimic natural bone and biomechanics, low profile hardware, different screw designs, resorbable screws that degrade over time once the fusion is solid, and coating hardware with growth factors. Look, I think if you continue to double click and push the model, what we're talking about here is a system that has 100 lifetimes of insight built into it, right? And the interaction between you as an expert and this synthetic cognitive system, maybe there are patterns there, right? So what's really exciting is that it's accurate. There's a ton of insight built into these systems, and it's up to us as experts and clinicians to ask the right questions. Who knows what's possible? And the value of these systems is borne out in the demand statistics. So this is a chart that shows how long it took to get to 100 million users for various platforms. So Netflix took 18 years to get to 100 million users. YouTube took 1.5 years. TikTok took 9 months. ChatGPT or GPT-4 took 2 months to hit 100 million users. This is a recent story. So 200 million people use ChatGPT daily. Right, that's how useful this system is. Out of interest, I ran similar kinds of jokes through GPT-4 to see if any, there are any improvements, and it got this knock-knock joke, and it was a little bit better with this one. So that's generative AI in terms of textual data. What about generative AI in terms of image generation, right? So this is a model called DALL-E 2. Essentially, what these models do is they take text. They create images based on that text. They've been trained on labeled images from the entire internet. So this again was a year or so ago. I asked it to create an oil painting of a neurosurgeon in an operating theatre in the style of Rembrandt, and this is what it came up with. This is brain anatomy in the style of Cézanne, neurosurgical anatomy in the style of Monet, and another example here. So really interesting artwork. Never before existed, entirely synthetic, created by an AI based on those textual inputs. At the time, I was impressed and excited about it, but then came along Midjourney. So Midjourney is, you could argue, the state of the art in image generation technology right now. It's been out for a little while, but it's still amazing in my view, and it creates incredible photorealistic synthetic images. it can illustrate, creates artwork, realistic people, amazing images, an incredible system, can be used for ideation, architectural designs, etc. So it's compelling, but interestingly, from a medical perspective, it's incorrect, right? So if you ask it to draw a picture of the brain, this is what it comes up with, not quite right. Some examples.
Oh, gross.
Yeah. I asked it to draw the circle of Willis, and this is what it came up with. And the basal ganglia, right? It's interesting artwork, but completely anatomically incorrect. It has no idea what it's doing when it comes to neurosurgical and anatomical imagery. This is what it thinks neurons and synaptic connections look like, right? So in our artist's depiction, this is what it thinks the cerebral vasculature looks like. This is cranial anatomy, beautiful, compelling, interesting, but obviously incorrect. I asked it to draw neurosurgeons in the OR, and you'll notice that it's not sterile. The masks are incomplete, and that doesn't look like neurosurgery. Here's another example, again, not sterile and not neurosurgery, right? We saw that ACDF example before, and we saw its ideas around creating new hardware. And so I asked Midjourney to give me some blueprints and ideas around designs for new spinal fixation hardware that could be used to treat, scoliosis, for example, and it designed me some new spines. So it's not quite there yet. So there are still, so we've seen, what is machine learning? We've seen current applications within neurosurgery, and we've had a look at generative AI in terms of text and images. There are still some challenges and issues that are thorny, that need to be worked through. There's a lot of very smart people working on these problems now, but we have some responsibility as clinicians to facilitate this process. Some ethical challenges that continue to exist, revolve around governance, confidentiality and privacy, mitigation of bias, transparency and accuracy and relevance, and legal challenges, revolve around regulation and liability. An interesting example, there are many examples of AI failures out there, and this is an interesting one. So Google's large language model Bard AI came up with an incorrect fact around the first planet photograph that was shared on Twitter, and that hit Google's stock price. So inaccuracy is still an issue. This is an interesting idea, right? So one of the kind of bastions of us as people is that this statement around people will always have empathy, and that will always be an edge that we have of artificial intelligence systems, right? But maybe not. This is an interesting study that suggests that ChatGPT appears to express more empathy and have better bedside manner than clinicians, at least when it comes to written advice. And you can see how that's credible, right? I mean, many of us are extremely busy, and it can take a lot of time and effort to communicate those ideas and that empathy in written content, whereas they're constraints that an AI system just doesn't have to deal with. So empathy may not be the sole preservation of a human. So let me wrap up there. I'll try to be efficient with your time. I really appreciate your attention. So we talked about, what is machine learning? We saw some examples of algorithms. We saw the supervised learning process. We got an insight into what it can do with a particular focus on neurosurgery and generative AI. And we've had a look at the near future and its potential influence on our specialty. I think some of the conclusions to draw from all of this is that it is powerful. It's an incredible technology, I think, and I think it's profoundly exciting. Some trends that we're noticing as time goes on are that systems are moving from narrow to comprehensive. So instead of creating an algorithm that just differentiates between complications versus no complications, we're seeing systems that can analyze an entire CT brain scan or an entire chest X-ray and classify over 100 findings. So comprehensive systems are the future. But we're also going beyond natural inputs and outputs, which I think is a really interesting thing to keep an eye on, right? So people have diagnosed Alzheimer's disease by processing retinal images, and people have been able to use chest X-rays to predict the likelihood of stroke, right? So instead of just using a CXR for the detection of chest pathology, we can use it for other things. And then this other example that I highlighted earlier, which was using MRI for glioma genotyping and classification, which could potentially, eliminate an entire procedure from the profession. Implementation of these systems is complicated and rate limiting. We've generated some ideas and guidance and frameworks around how that can be done, and others have built better ones. There are lots of issues to consider. It's interesting, Geoffrey Hinton said a couple of years ago that people shouldn't study radiology now, right? Because it's going to be automated in 5 years. He was entirely wrong, right? And the reason is because these systems, yes, they're capable. The CT system that you saw earlier, it's capable, but these technologists are not healthcare experts, right? They're not familiar with the regulatory environments. They're not familiar with the change management process. And so I think, as I mentioned before, these changes are less about automation. It's much more complex than that. And it's about facilitating efficiency and quality improvement. I think change is going to take a lot longer than some people might expect. AI is not a monolithic single scientific breakthrough. It permeates everything, and it has the potential to permeate all aspects of neurosurgical practice. And I strongly contend that our capabilities are complementary, right? It's about augmenting us as clinicians. So how can you learn? How can you get involved? Feel free to take pictures of these resources if you'd like. Many reviews have been written on this topic that are useful. Some help us to critically read the machine learning literature, to look for gaps and problems and push for continuous improvement. And many of these other reviews focus on particular aspects of the neurosurgical specialty, and we've written a few on different aspects as well. These are some excellent books on the topic. So the alignment problem I can recommend as a particularly good one. It reviews a lot of the science from the 70s onwards and gives you, a fantastic contextual understanding of where we are now. I highly recommend that book. This book is also fantastic, AI Superpowers, and gives you some insight into the geopolitical issues that revolve around this huge AI revolution. A couple of other books that are more recent. So Mo Goddat's book, Scary Smart, is interesting. And I think this one by the co-founder of DeepMind is going to be exciting as well. It was just released. Some podcasts that I recommend. Twimmel AI is really good. Practical AI is a great one. AI with AI is also a good podcast. And there are plenty of websites where you can learn how to do this, what it means, and you can play with GPT-4. So it's going to require a close partnership between data scientists, engineers, and clinicians for us to do this successfully. Just remember that this is all about prediction and classification. It's based on 3 core factors: algorithms, compute, and data. It's based on the programming language Python. And if there's one thing you do after this presentation, I'd recommend doing what you can to learn this programming language, because it will give you access to this revolution. So let me close by saying that machine learning enables accurate diagnostics and outcome prediction, which facilitates better clinical decision-making and healthcare efficiency improvements fundamentally. The impact, utility, and power of machine learning are clear and are reflected in the explosive growth in applications and publications that we've seen. Machine learning has the potential to permeate all aspects of neurosurgical care. Generative AI systems have the potential to drive innovation in neurosurgery. And synthetic intelligence is a new form of capital, and there's a race to control it. But as we saw, AI systems are powerful, but they're not perfect. They still require scrutiny by experts, and they require experts to guide their development and implementation. Notice how this watercolor image that I asked Midjourney to create has a 3-winged bird. So, join me in facilitating the implementation of this incredible technology into healthcare. If we as clinicians, with patient care and patient safety as our guiding North Star, don't guide this process, then who will? I'm excited about this technology. I think it's an incredible time to be a clinician. Thank you for your time and attention. It's a real honor and a privilege to be here. Thank you.